So the topic is about discovering band order dependency. My name is Pei Li. This is a joint work with Yarik, Michael, and Divesh. Order dependencies are common relationships between attributes in datasets. For example, this table stores real-world music releases with attribute ID, release year, month, and catalog numbers. When sorting the table by catalog numbers in increasing order, if we also observe that the year is also in increasing order, we say that there is an order dependency between catalog number and year. However, in reality, this may not always be true. As seen in the table, T2, T4, and T7, they violate the dependency. So there are two reasons causing the violation. First, erroneous values are introduced to the datasets due to data quality issues. Second, there is sometimes delay between the generation of the catalog numbers and the release date of a record. So catalog numbers are often assigned to a music record at early stage of the production, and the lifespan of producing a music record varies from a short period of time to up to a few years, based on the complexity of the product and the available resources. In this talk, we would like to introduce a new order dependency to identify data quality errors while still being tolerant to small violations to the traditional order dependencies without actual violations to the application semantics. So formally, we introduce a new dependency called band order dependency. It specifies that when tuples are ordered increasingly on the left-hand side attributes, in this case, catalog numbers, the right-hand side attribute, in our case, year, must also be ordered non-decreasingly within a specified bandwidth delta. So let delta be 1, then it means that each tuples can only violate the order dependency by maximum 1 year. Given delta equal to 1, we can say that the band order dependency between catalog number and year is satisfied in the input dataset, except for tuple T2. So as mentioned, in real-world applications, band order dependency often hold approximately with some exceptions due to accommodated errors. We say that the dataset approximately satisfy a band order dependency if there is a few number of outliers that violate the dependency. We quantify such a few amount of outliers with a predefined percentage threshold. So our problem is to automatically identify whether a band order dependency approximately holds in a given dataset. So the key to approximate order dependency is to identify which attributes of the records, to identify which subsets of the records are outliers and which satisfy the dependency. So to this end, we introduce the notion of longest monotonic band. So let's revisit a motivating example in 2D dimensions where the x-axis represents records index ordered by catalog numbers, for example, T1, T2, and T9. And the y-axis represents the releasing year. So for each two tuples that satisfy the predefined band order dependency, we can always draw two increasing or non-decreasing lines so that the two tuples are inside the space between the two lines, and the distance of the two lines are within a bandwidth delta. So we call such subsequence a monotonic band. If we put all the tuples satisfying band order dependency together, we get a longest monotonic band. So once we found a longest monotonic band, it is easy to identify which tuples are outliers, and obviously we know if an approximate band order dependency holds in the input dataset or not. So note that if we set the delta equal to 0, such a longest monotonic band is also called a longest monotonic subsequence. So now the key to our problem is to construct the longest monotonic band in the input sequence. The good news is that the longest monotonic band solution has an optimal substructure property. Let Ti denotes the subsequence T1 until Ti, and Li denotes the length of longest monotonic band in subsequence Ti. The optimal substructure property suggests that the longest monotonic band in subsequence Ti is determined by the longest monotonic bands in subsequence T1 until subsequence Ti minus 1. So therefore, for each tuple Ti, we need to check whether it can extend existing monotonic bands in subsequence Ti to subsequence Ti minus 1. So again, we demonstrate on the motivated example. Given the input sequence of tuples, each of which is represented by the releasing year ordered by catalog numbers. So we scan the tuples in sequence while maintaining two arrays. The first one stores the maximum tuple in subsequence Ti, and the second one stores the length of longest monotonic band in subsequence Ti. When proceeding the first tuple, we get a longest monotonic band of length 1 with maximum tuple 1992. So now we proceed to the second tuple. Obviously, it can extend the existing longest monotonic band. So therefore, we get a new monotonic band of length 2 with maximum tuple 2012. Similarly, we also update the two arrays for the third tuple. So till now, we have two longest monotonic bands of length 2, each with different maximum tuples. So now for the fourth tuple, we'll again check if it can extend existing monotonic bands by comparing its year information with that of maximum tuples. So the new tuple can extend a longest monotonic band of length 1 with the maximum tuple 1992. It can also extend a monotonic band of length 2 with maximum tuple 1996. Since we're looking for the longest monotonic band, so we take the second band. Note that in the second case, the new tuple violates the traditional order dependency, but band order dependency still allows a small violation of 1 year. Therefore, we get a longest monotonic band of length 3 with the maximum tuples remaining to be 1996. So we proceed the rest of the tuples accordingly. Once all tuples are scanned, then we found the longest monotonic band in the input sequence has a length of 8. So by scanning the length array reversely, we can easily construct the corresponding longest monotonic band. For experiment evaluation, we compare our proposed approach longest monotonic band with baseline longest monotonic subsequence, where we set delta to be 0 over real-world datasets, where we know the ground truth, as well as synthetic datasets, where we inject errors by randomly modifying the year information. We measure the result by precision, recall, and F measure. Our proposed approach dominates baseline over real-world datasets. It dramatically improves precision as we are very tolerant with small violations to the traditional band, to the traditional order dependency. So with controlled errors injected to real-world datasets, our proposed approach actually achieves higher F measure for the reasonable amount of noise. We also vary the bandwidth parameter from 0 until 20. While setting it to 3, our solution obtains the highest F measure. This is consistent with the application semantics, as there is often a few years of delay between the generation of the catalog number and the production of the music releases. For future work, we plan to extend our existing work by considering not only approximate but conditional dependency, which are satisfied over subsets of the data. We would also like to consider increasing and decreasing orders. In addition, we will improve the efficiency and automation degrees of our solution. That's all. Thank you.